it. Let's see. Yeah, it's working. Okay. Cool. Right, so today we're going to talk about linear models for regression. So there is a good reason to not call it linear regression, because linear models are so much more expressive than a simple linear combination of features or input, so to speak. And we will start from that. Because I think most of you would have taken either IML, Intro to ML, or some statistics course, or even generalized linear models. And most of you already know what linear regression means. For example, the first picture in the cartoon. And those of you who have taken generalized linear models will know that at least you can put a nonlinearity on the output and make the model able to fit a richer set of functions. So what we're going to talk about is linear, essential linear models with basis functions that can, in theory, fit any hypothesis or any function that we would like to fit. So before we get started, I would just like to reiterate the message on Piazza. Assignment 1 is released, and it's due Monday, week 6. It has 2 parts. The first part, what we call theory part, is a set of derivations that leads you to work through beta Bernoulli distributions, right? Or beta binomial distributions, basically the Bayesian treatment of coin tosses and how conjugate prior works. You should be able to get started on this now. I highly recommend it. And then there are 2 sort of groups of questions in the programming part. That also has a few latex blocks to get you sort of think mathematically about the problem. So the first one is Bayesian linear regression, which you should be able to do after this week. And then the second block is neural networks, which is quite simple, I would say. Takes some time to do. The content will be covered in week 4, and feel free to get started early. The reason I'm saying that is also that assignment 1, I would say, is a significant in volume. So do not wait for the last week or last minute. I think also our purpose of designing this assignment is also to give you something to exercise your mind on, give you early feedback. And we all know that students tend to get busy in the second half of the semester. Therefore, we front load some of the work. Right, so we know that most other courses don't have an assignment so far, so get started. There's another assessment item coming, basically a 2% hurdle quiz that will be due in week 5. You can expect to have a short window of time to work on it, and it's open book, right? So more about that will be available in meantime. We expect to have the quiz question sort of done in week 4. It will probably be released early in week 5, right? And it will cover basically material roughly in the first 4.5 weeks, right? Yes, the programming and theory part, the total of assignment 1 is 25%. The theory was 12%, and the programming is 13%. So there are some gray value that's written in the assignment sheet. I think they are each 100% points or something. They will be renormalized to these fractions, all right? So here's our plan for today. We will start from an intro part talking about the rationale behind linear models and basis functions. The next block of essentially big blocks of content is essentially maximum likelihood estimate for least squares. You will see that maximum likelihood and least squares actually are inherently connected. They are the same model. We'll have a look at the normal equation again. We will then look at regularized least squares, which you saw in like last Friday, but you will essentially, the spoiler alert is that regularized squares has a connection to Bayesian linear regression, which we will see on Friday. We won't quite look at multiple outputs, but it's a good example of problem simplification or reduction. We'll spend some time looking at what's called bias-variance decomposition. So this lecture, I would say, is a bit long. We expect to take the full hour and a half, so pace yourself. So a brief intro. So why do we care about linear models, or why is it a good idea? It's because, right, linear models are good. So I'm going to push the story further to say that it saves lives, and that's true. I have a baby who is about 1 year old right now, 14 months to be exact. As I learned towards essentially the date of having the baby, there is something called APGAR score for babies, for newborns. Turns out the most dangerous moment in most people's lives are the first few minutes of their lives, right? So what the APGAR score, designed by Virginia Apgar, a doctor in New York, is essentially a linear combination of a number of simple measurements that can be done in a snap of a second in order to assess whether a newborn baby needs intensive care or needs attention or is mostly healthy, right? You can see that there are 5 factors that are sort of back into the last name of the inventor, like skin color, pulse rate, and so on. And each of them has a number of features that maps to a numerical value between 0 and 2, and then they are simply added up. The reason for this is, it will be quick for medical professionals to map these physiological features to like 3 sets of scores. These are distinct scores. And then it's very quick for people to add them up, right? So a score of 6 or less at 1 minute after birth, or a score of 7 or more at 5 minutes is normal. Otherwise, more attention is needed. So this is great. And more generally, linear models are liked because of their simplicity, and simplicity has long been one of the driving principles in science, right? Albert Einstein has this famous quote that a lot of you would have seen. In machine learning, people quote what's called Occam's razor a lot. It's also called law of economy or law of parsimony. It states that plurality or complexity should not be posited without necessity. Right. So linear model is one of these models that are very simple. I will also preface the whole discussion by saying that, yes, while being simple, elegant, and practical, linear models are not without their drawbacks. So, for example, modern machine learning systems, even in the medical fields, I wouldn't call it machine learning to be specific, but they are composed, right? For example, back to the topic of newborn neonatal risk assessment, right? So the APGAR score is a component to more advanced scores. I'm mentioning two of these, right? One is called SNAP2, and yes, different versions. SNAP has ALCA score as a component, and it has a number of other more detailed measurements. So another score that's developed in UK that's well known is called CRIB. What this particular research article published in the Lancet, the top medical journal, basically says is that the CRIB is sort of appropriateness of CRIB after a number of years or a decade or so, that needs to be calibrated, right? So as neonatal intensive care become more commonplace, the probability estimates or the estimates for the original CRIB seems sort of inaccurate. So this goes back to the point that, yeah, when there is a distribution shift in the data, the model needs to be reconsidered or monitored constantly. Okay. So there are also, beyond philosophical or conceptual reasons for preferring linear models and practical reasons, there are also analytical or mathematical reasons that linear models are good, right? So, so when there are like slide blocks with a yellow header, they refer to, like you'll find the original or the longer version in the last year's slides. It's also mentioned in the book, right? Basically, if the goal is to minimize sum of error, square error, then we have analytic solutions. Analytic solutions are good for computation or for understanding, right? The statistical behavior of linear models can also be understood and analyzed in detail, as we will see in bias-variance decomposition, which we won't be able to do in many other models. And also there are efficient algorithms exist for convex losses, and we'll see basically the notion of convexity is important in machine learning. It leads to efficient algorithms with guarantees and regularizers, and like basically you can put regularizers and it's still well behaved, right? So what does it mean, right? Linear models, we can like for vanilla linear regression, we think of say input traits as x1 through xd, and then the output y is parameterized by w, is a simple linear combination of them. And w0 is called the bias term. Again, the word bias does not carry like positive or negative connotation, and it's equivalent to having essentially an x0, like an additional constant feature that is always 1. And this is preferable for many reasons. One reason for that is that we can write the whole expression now, if we pad the input with a constant of 1, as essentially an inner product between the weight vector and the input vector with also, it's conventional to like write the first, like we can write features as phi's, and then phi0 of x is a constant of 1. So geometry of padding, the geometry of padding 1 is as follows. So suppose we have x's living in 2D space, right? x1, x2, and there are two groups of points, right? Like this, the green point and the red point, right? So these y expressions, they are essentially shooting rays from the origin, right? So the different w vectors, they are essentially different rays, are all from the origin. So we can see that some of the green dots and the red dots lie on the same line, same ray, and that's bad. But if we essentially, what we have done is we have the same points, right? The green and the red in here, and x1 and x2. If we essentially add 1 to a new dimension, call it x0, now we have moved essentially the whole data plane to somewhere away from the origin. And if now we learn W that are also essentially shooting rays from the origin, we can see that the green points, so the green blob would have been here and the red blob would have been here, and then we can separate them essentially. So this will be more clear when we're doing classification. That's an important intuition. So for this lecture, we're going to denote essentially feature input or basis or so-called basis functions as the vector of phi of x, as we will see in the next 2 slides. So in the convention of our textbook, so boldface x denotes the original input. For those of you who are familiar with stats or R or Excel, you can think of X's as basically spreadsheets, right? So rows can be different data in data points. And then columns are input dimensions. So we can think of it like this. Right, so these are the first row, maybe column names. And then the first column might be like data indexes, right? Data I goes from 1 to n, and then these are values, right? We also think of them as in like the original input space. I'm just going to draw some data points, right? And it might lie like that. So the picture on the right shows a bunch of data points that we might think of fitting a line on them. But on the picture in the middle, you can see that fitting a line is difficult. So if then we transform these x into phi of x with basis functions that are nonlinear, we'll talk about them in the next slide, we can essentially think about, we essentially bring x into a higher dimensional space. Just like in the previous slides, we turn the, say, 2-dimensional x by adding 1, and that will become a 3-dimensional input space. In here, we can essentially transform x and have an arbitrary number, like arbitrary dimensioned feature space, right? Once we have a high-dimensional feature space that were essentially still driven from the original input in low dimensions, then in the original input space, we can have nonlinearity, such as this one drawn like in this sinusoid, in this feature space, right? So in order to fit a sinusoid with a linear model, we have to bring x into a higher dimensional space. And the way to do so is with different feature functions, phi. So here are a number of feature functions. So the first one we might think about can be polynomial feature functions. We know from calculus that polynomials, right? If we do a Taylor expansion on any function, they turn into polynomials, right? And therefore, polynomials are good universal representation for functions. So we can do that. And we can basically decide a fixed order of polynomial that we want to fit and then use them as basis functions, as we saw last Friday with the curve fitting 101. The catch is that polynomial functions, they by default all blow up, basically have infinite volume, magnitude at either end when the input is either really big or really small on the negative side. So if we try to extrapolate, if we try to interpolate from polynomials, that's doable. If we try to extrapolate, then the value of the function will essentially become unbounded. Right. So an alternative can be Gaussian basis functions. Gaussian here is in quotes simply because the basis function essentially is proportional to the exponential of the negative square distance between where the function is evaluated and some data point, right? It doesn't have to be normalized, and it's not a probability distribution, so its volume can be scaled up and down. And it doesn't need to be normalized because it's taken care of by the model parameter W. So it is well-behaved in this case, where well-behaved means that the magnitude of the function is bounded, but the catch is that they're pulled to 0. So if we're trying to extrapolate using Gaussian basis functions, when the data point, the test data points are far away, the function value will vanish. So what about other alternatives? For those of you who have seen neural networks, most of you have, you will have known the sigmoid function. That basically is sort of a smoothed out step function, so to speak. And a variant of that is a hyperbolic tangent tanh function, which is just a shift of the sigmoid. And that can also be used as basis functions. So in there, on one end of the infinity on the left-hand side, it vanishes to 0. On the right-hand side, it vanishes to 1. So for those of you who have an engineering or physics background, you would know that other basis functions are possible. If we're trying to fit the sinusoid from the start, then we can actually have sine and cosine basis functions that are universal due to Fourier transform and real valued cosine transform and so on. You could also have wavelet functions that are essentially generalizing Fourier in the time and frequency space. You can also have splines that are essentially piecewise polynomials that are smooth when they are joined. And it's only defined on a input interval, fixed input interval, so that it's well behaved. Right. So these are basically a menu of choices of common basis functions. Other basis functions are possible. So now, the equations on the top in here. So let's look at how to define a likelihood of linear models, right? The equation on the top we already saw. The two equations at the bottom essentially allow us to define a likelihood. If you stare at the picture on the right, we saw it last week on the probabilistic view of curve fitting. Basically, the mental model for here is that at each point of the learned curve function, the output t is the regression function, y of x parameterized by w plus a noise, right? So measurement noise and so on. And furthermore, we said the noise is parameterized by the variance or precision parameter beta, right? Yep. So this is, not a strong assumption. It corresponds to this blue bump around the fitted curve. So now let's compute data likelihood and then see what the maximum likelihood solution is, right? In here, if we have one data point, the input of x, output of t, the probability of observing the output t given the regression function, assume w is known, is this normal form, 1.60, right? And then if we have a range of input and output tuples. Essentially, we have xi and ti, xi as vectors, ti are scalars, I goes from 1 to n. We will have this expression in the middle. Because the xi's are and ti's assumed to be independent of each other, xi's are ID, then the probability of observing the whole vector is simply a product of the individual probabilities. Yeah, staring at this big product sign pi, it's conceivable or convenient. Often throughout this course and elsewhere in statistics to take the log of the product to turn it into a sum, right? So that's what we're doing. So we simply take the log of the likelihood term, and the product turns into a sum, and then the log goes inside. Basically, then we're essentially logging the Gaussian probability term. Then the next step, we're simply expanding this univariate Gaussian term into its constituent parts, right? So we just write out the normalizer is beta over 2 pi taken to the square root, and the exponent is beta over 2 times the square distance between target t and y of the regression function y of xn and w, right? So if we go to the next page, right, the first two lines were from the last page. We're now simply expanding the log term by, well, log of a product is the sum of the individual pieces. The first piece is log of beta, and right, it doesn't change with respect to data points, so there's a factor of n. Is there 1 over 2 missing here? Yeah, and then log of 2 pi is a constant. There's also 2 over n. And then the last term, the square root. So log and x cancels. The constant beta comes out front. And we're essentially looking at a sum of square terms, right? In here, we see the familiar sum of square error function after taking the log of the Gaussian probabilities. So here the claim that I'm making in this slide, and we will back that up in the next 2 slides, is essentially the maximum likelihood solution. This is maximum likelihood estimate of W, vector W, is the same as minimizing the square error. We can see that by eyeballing expression 3.11 here. Basically, this is the only term that depends on W, right? The square error term is the only one that depends on W. So that's intuitively makes sense. And now we just need to solve what it is. So in last week's lecture, we did present an estimate for the bias term and beta, but we didn't actually solve W. Let's now do that, noting that the solution is basically the same between maximum likelihood and least squares. So this is just the square error term written out again. And it is convenient to write it out in matrix and vector notations. So let's unpack it a little bit. When we see a sum here, basically a sum of squares can be unpacked as the inner product of 2 vectors. And here the 2 vectors are essentially t and phi times w. So this big matrix phi is done by is composed of simply the feature values of each data point, right? So this is data points. If I circle a row here, this is the second data point, x2, or yeah, essentially phi of x2, right? And if we circle a column here, this is the first basis function for all of the data points, right? Sometimes this is denoted as phi I. And then it's basically the first basis function, whether it's sinusoid or Gaussian or whatnot, for the first data point x1, for the second data point input x2, all the way to the last input x of m. We verify, well, this inverse product by basically mentally unpacking it as T transpose is a row vector, right? And then phi is this matrix, and W is a column vector. Right, and that transposed is another row vector. So basically this term is a row vector, the second term is a column vector, the inner product of it comes back to a number. Right, so if we plug this matrix expression to the log likelihood term, we essentially get this last term, right? We take the gradient with respect to W. As we said 2 slides ago, the first two terms don't depend on W, they're just constants and they vanish when we take the gradient. Referring to our matrix cookbook, you will get essentially gradient of these matrix terms, but more intuitively, so this vector inner product is roughly as like quadratic term of W, right? Where each of the T minus phi W term is a linear term of phi W. Due to chain rule, so we basically have, if we take the gradient or derivative of a quadratic term, we get the term itself, which is T minus phi W, and then we get we take the gradient of the linear term, which results in the phi term in front, right? So we're trying to find stationary points with respect to W, so setting the gradient to 0 gives us essentially multiplying these out. Beta don't matter, again, it's a constant. Phi transpose T minus phi transpose phi W, right? Moving phi transpose T to the other end, right, like this, we can see there is a phi transpose phi in front of W, then what do we do, right? Phi transpose phi is essentially, so phi transpose is, let's say, D by M matrix, and phi is a like M by D matrix, and this is like D by D matrix, right? Right, again, matrix algebra, you just, this D by D matrix happens also to be positive semi-definite and symmetric, so we can invert it and essentially multiply the inverse in front of both ends, and we get the normal equation here, 3.15. Right? So let's try and understand the normal equation a bit more in the next few slides, all the way until the geometric intuition part. Basically, if we look at the bias term, basically the term that multiplies the constant feature of 1, we can see that, well, the exact derivation of this in the book, that basically the bias term is a difference between the average output to the average of the, so basically xj and w of the regression function. So basically the bias calibrates between, right, essentially the sum of the average of the output and the function we're being being learned without the bias term. So that makes sense. That's what bias means. It's just a constant shift. Moreover, we can estimate beta, which or 1 over beta, which roughly correspond to the variance of the regression of the output with respect to the function. And the estimate of this is essentially average squared deviation of the regression function to the output. That also makes intuitive sense, right? So what about, right, the normal equation itself, the majority of it? So what we can do is we can try and interpret it in the matrix space, right? So assume we are in a space of the training, well, that are generated by the training points. So we essentially unroll the regression function y of x comma w using the maximum likelihood estimate of w, right? So if we look at WML transpose of phi of x, we can see that this phi1 is essentially the first feature function on the first data point, a vector of the first features on the second data point, and so on, phi of x. So what happens here is that we look at the n-dimensional space spanned by these feature functions. And the vector t, the target, is actually unconstrained in this space. So it may, and if we project t down to the space spanned by these feature vectors, then y is the projection. So in other words, right, the fact that y is a linear combination of these phi vectors says that y is in the subspace spanned by these phi vectors. And then the fact that y is a least squares estimate of t, recall from linear algebra 101. Well, if you don't remember, feel free to look it up. That basically the projection onto a subspace has the least squares, right, in this sense, right? So that's the intuition. There, so this geometric intuition is quite elegant. It might be hard to wrap your head around sort of on the first go. So feel free to read a book. And there is another YouTube video that essentially derived the normal equation using purely the geometric intuition, and it's quite cool. What the normal equation also tells us is that the good news is that we, as some of you said, there is an analytical or closed form solution of the maximum likelihood of the weights given the input. But the bad news is that there is a matrix inverse, right? We see that this matrix is symmetric and real, right? It's one of the quote unquote nicer matrices, but it can still be close to singular, right? So this is, so when this matrix is close to singular, or basically some of the eigenvalues close to 0, then inverting it is going to be a numerical nightmare, right? And this is also what yield condition means, right? More precisely, yield conditions refers to the ratio of the smallest to the largest eigenvector value. So when that happens, right? So when this matrix is almost singular, then numerical algorithms will have problems. There are ways to overcome it. We will see one in a little bit, like regularizing helps. We can also use tricks that you will practice in the labs after the PCA lecture, basically SBD. So I would just add a footnote to this like maximal likelihood for regression section. So what we just covered here is called batch learning. Let's say in this like day and time, you almost surely would have heard of it if you have looked into neural networks. The reason that it's called batch is that these 5 vectors encode all the input, all n data points. And we're solving for one value of W involving all input. This is nice, but when we have millions of data points and so on, then solving for this can take a while, right? Can be computationally kind of demanding. And especially there are also cases when our data points comes in one or a few at a time, then we would like to be able to update our weights given the new data points, or basically learn sort of start from some W and then move towards a better W as we go through the data. This is called stochastic gradient descent. Again, machine learning is full of names that have a particular meaning in a given context. In here, well, the word stochastic here simply means that the estimates of the gradient at any data points depends on the small number of data points, like one data point that we're looking at. It does not mean like the inherent stochasticness of the process that generates the data, right? So how this works is we start from some W, and then after seeing each data point or each mini batch of data point, we update W by essentially moving to a direction that sort of makes the sum of square error smaller. Basically, we multiply the feature vector of, or the kernel vector of the input with the error of that particular input. And this eta parameter in here is so-called learning rate, and it controls how fast we go down this essentially noisy gradient slope. We will see more of this in backprop neural nets. So in here is just a footnote and essentially prompt to that section of the content. So far we've covered maximum likelihood and its connection to least squares for linear regression. Is there any questions before we move on? There's no questions on Vigendran has a question, or no? If you have a question, feel free to speak up. Otherwise, we will let's talk about regularization. Okay. Yeah, let me just clarify. What I said wasn't that x and t are independent. What I said was the xi's are independent of each other. Sorry for that misunderstanding. Yes, the target value are dependent on input values. Hopefully that's clear. Okay, great. So also last week on Friday, we said, well, the symptom that we observed then was that the weights W blow up quite badly. And we wanted to sort of constrain the values of W so that they are close to the origin. So we wrote this particular equation 1.4 or also 3.27 in here. We didn't solve for W, but the solution, if we follow essentially the essentially we follow the MLE recipe we will get a variant of the normal equation. The second term is just the normal equation that we saw a few slides ago. And the first term inside the inverse here is due to regularized. It's due to the regularizer, right? So, so what does this mean, right? So I'm not going to go through essentially the same motion again, deriving this, but let's look at the intuitions behind this one. So first, let's look at the regularizer term. What we did was, we looked at regularizing in the L2 sense, right? In here, like W transpose W, the inner product of the W vector is essentially sum of its squares of each component. So it's this one. It's this one, L2 regularized. We can see that, so in this figure 3.3, the x and y axes are dimensions of W's. In here, we assume there are 2 dimensions. The contour line, again, the regularizer is, when W is 2-dimensional, it's a 3-dimensional mountain, right? The contour line here is circle, like the center of the circle is higher than the side of the circle. And when it's a L2, then it's essentially half of the sphere. When the regularizer is linear or Q equal to 1, we can see that the contour line are like they are lines because these are linear functions. So this is essentially a pyramid in 3D, right? And then, so for Q less than 1, it's a concave pyramid squished towards the inside. And then when Q greater than 2, it's essentially a sphere, but stretched towards the outside. So these are the intuitions about regularizers, Q norm regularizers of different order. So what does this say about like the normal or regularized solution of W, right? Before we look at that, let's first look at what's called Lagrange multipliers. So this is our first encounter to this, and we'll see more of it in kernel methods. So we're just going through a few key intuitions here. So the definition of Lagrange multiplier is that if we would like to, say, minimize or maximize the function subject to an equality constraint, g of x equals 0, or sometimes an inequality constraint, it's equivalent to minimize the same function, well, the linear combination of f and g modulated by the Lagrange multiplier lambda, which is a constant. So this can be counterintuitive. So what? Right. This is the first part of Appendix 8. You can read about it. But basically, what it says is that g of x equal to 0, or in our case, the w lying on, let's say, a circle, or like a diamond shape, is equivalent to a curve, right? This red curve in the space of x, or in the space of the weights in this case, right? So any essentially high-dimensional equation, right, is a curve in the space of x. So we can understand that. So what the claim of this key intuition says that there is conditions of the gradients of f and g that needs to be satisfied at the point that, like, let's say at x star, that's at the stationary point of for L. Actually, let me wipe out the star to be consistent with the graph. So suppose this XA is a stationary point, then the claim is that the gradients of F and G are lines up, right? They're either parallel or anti-parallel to each other. So the gradients of G is orthogonal to the surface, right? Because the surface is Gx equals to 0. If the gradient is not orthogonal to the surface, then essentially what this says, if we move along the gradient, the surface, the value of G does not change. That means essentially the fastest way, or the gradient, to change the value of G is perpendicular to the surface. Right, so this argument has nothing to do with the L function upstairs, but basically for any surface, the gradient of surface is perpendicular to it. This is also, say, calculus 101. And then the gradient of f of x is at the stationary point is also orthogonal to g of x in this particular case. Because otherwise you wouldn't be maximum or minimum point. So basically, right, so the combination of f and lambda g is 0 because it's a stationary point of L. And then f and g has to line up either parallel or anti-parallel. What this means is, like, here's a graphical example of the Lagrange multipliers. If we treat these blue circles as the contour space of weights, W, that we're optimizing, and then the red line is G, then the optimal point have to be where the red line and one of these contours is touching. Like, where it is touching exactly is up to the particular data set we're given, but it's basically, well, when they're touching, then that gives us the regularized solution. So the next plot, figure 3.4, essentially reiterates this, right? So the blue contour circles are essentially, contours of weights. And then the red line plus the shaded red circle and diamond are the surfaces of the regularizer. In general, the weight, the contours of the square loss function are ellipses, right? But we see that, well, from this intuition of Lagrange multipliers, the optimal solution W star regularized is where the ellipses and the regularizer surface or contours is touching. So for the L2 regularization on the left, W star tend to be a point that's not sparse, in a sense. It's hard to get line up the two surfaces so that they're touching exactly at the one of the axes intersections. But if the regularization surface is pointy, such as the diamond, then it's more likely that they're touching either close to or exactly at the surface. In which case, we say that the solution of W is sparse, meaning one of the weights or some of the weights are close to 0. This is preferred, especially when we have large number of basis functions or the feature dimension is very high. Okay, so that's the part, geometric intuition about regularized least squares and what's happening. What also happens when we regularize is that this matrix, lambda I plus phi transpose phi is now better conditioned, right? So each of the eigenvalues, it's at least lambda. So going back to the matrix codebook, right? For symmetric matrix, if we add lambda I to it, then the eigenvalues are also like lambda is being added to each of the eigenvalues, which is rather neat. And inverting it is hopefully an easier job if lambda is not too small. Right. So about multiple regression outputs, there is I don't have much to say aside from so the derivation is quite mechanic. It's a good exercise in matrix calculus, but the key takeaway is that it actually reduces to multiple univariate regression problems, which is neat. And it also says that, well, when a more complex problem reduces to a simpler problem, then knowing the simple problems is sufficient. Great. So is there any questions so far? We're going to dive into the next bit of content talking about like decomposing bias and variance in linear regression. Okay. I take silence as in people are okay. So bias and variance are sort of two fundamental concepts in understanding the behavior of machine learning algorithms. And they are different from the phenomenon of overfitting, like we talked about last week. So on the web, there is quite a number, like a lot of cartoon picture of bias and variance. And in the next 20 minutes or so, we're going to make it more concrete, right? So ideally, assume the red dot in this picture represents the true model that the data was generated from, right? Ideally, we want different estimates, basically the different little blue dots, to land on the bullseye, so to speak. And if they are all like the columns or the columns of low variance refer to the fact that the different estimates, the little blue dots are close together. The rows of low bias refers to the fact that they are all close to or lies within the target region. So there can be a few different cases, meaning we can have high bias and low variance, right, in the lower left, meaning the different estimates are close to each other, but they're far away from what the true generating model is. One could have low bias but high variance, meaning the different estimates are sort of, the variations across different estimates are big. But on average, if you sort of average them, hopefully they are still close to what the true model is. And of course, the worst case is high variance and high bias. So, in machine learning, bias a lot of times comes from a misspecification of the model or a model that's not expressive enough, right? So what are the sources of different dots, right? So if the model specification is too simple, such as what we looked at last week, trying to use a line to fit a sinusoid, then we're going to have high bias. Right? And then the sources of variance usually comes from different data sets or different data subsets. So as we covered, and it also can also come from randomness in learning, meaning we may have different initializations, or stochastic gradient, meaning that the gradient descent doesn't follow a deterministic path, and we might end up in different parts of the optimization landscape. But it does not necessarily just limit to initializations. So what this also says is that when we're conceptually trying to analyze how the learning algorithm is doing, it's beneficial to think about what are the sources of randomness and changes across different runs of learning, so that we can disentangle different concerns, such as randomness due to data or randomness due to optimization or due to initialization. All right. So in this particular section, or in the linear regression case, there is a clean view of that decomposes bias and variance, and we will be mainly concerned about variance due to different data sets. Because as we covered, there is an analytical or closed form solution. Given the data set, the solution should be the same. Okay, going back to the familiar picture of this regression function and the estimate and the noise around it, right? Right, so the regression function y of x is minimized by taking the expected square loss. Basically, I wouldn't derive it. There is a, right, like a calculus of variations way where you can formally derive this. But informally, when we assume that our data is the regression function plus noise, the best estimate we can get for the regression function is the mean of this conditional distribution P of t given x, right? So let's just take that for granted. That was in chapter 1. And then we essentially rewrite it with a slightly different notation in chapter 3. Now it's called h of x. It's an expectation of t given x, and we can write it out formally like that. Note that this is a function of x still, because we've only taken the expectation with respect to t. Now something interesting happens. This allows us to take the expectation of the loss function, or the square loss function, which is y of x minus t squared, taken over the distribution of both x and t. And given that we said y of x is conditional expectation of t given x, we essentially just plug it into this expression. What we did here is a common trick, again in machine learning. We'll look at it in several parts. So when we are concerned with the square distance between y and t, we expand this term by adding and subtracting the term e of t given x here. It might be hard to know what to add and subtract at the beginning, but let's look at a few instances. Hopefully we'll get a better idea. And for now, we're just assume someone told us to add and subtract this particular term. And if we just expand the squares, we just essentially group the first two terms and the last two terms. There are two square terms, and then there's the cross term, right? So for this particular cross term, we see that we multiply the difference between y and the expectation, right? And the expectation of t given x and t. So this middle term vanishes as we know that, y of x is essentially expectation of t given x. So then the expectation of the loss function becomes the sum of the two square terms. So the second square term, back to this picture, is the expectation of t, which is, say, here, expectation of t given x, minus t squared. So this term is noise. So given this model of a regression function, there's not, this is an inherent uncertainty of the model. So as we remember from a few slides ago, the variance is parameterized by 1 over beta. And there's not much we can do about it. What we should look at is the first term, right? Moreover, so the book makes a note about if our loss is not squared, what the geometries look like. For square loss, it's the quadratic curve, but if the order, like norm order goes up, the loss is more steep. When the norm order goes down, it becomes less steep. And when it's less than 1, it sort of tapers off for bigger values of the loss. And these intuitions are important for designing loss functions and advanced methods, essentially. And it's also important for example, to understand the link function or the nonlinearity for neural networks, right? So okay, so what we are looking at now was the sum of the two square terms 2 slides ago. We now plug in h of x into this, right? Right, that basically what we did was just to replace expectation of t given x with h of x. And what allows us to decompose bias variance is to consider different data subsets of D, right? That we denote as curly D. So let's do that. So basically, in addition to dx and dt, now we have taken the expectation with respect to we're taking the expectation with respect to data subsets D. And now we use the same trick of adding and subtracting the expectation of y of x given the data subset D over the subsets. So as said, we use a lot of expectation signs here, which exact variable they are taken over is important. In this case, assume we do this. Again, it breaks down into 2 square terms and also a cross term, right? So in here, in 3.3a and 3.9, the expectation is taken over data subset D. The cross term disappears because the first term also goes to 0. Now, the first, this term over different data subsets, D, translates into the sum of two squares again, roughly, right? The first term here is the expectation over different data subsets between, between the mean of different estimates over different subsets and h of x, right? So h of x is the true estimate. So we call this the bias term, right? So a graphical picture, back to the toy, like cartoon view, is that if we have different estimates as blue dots, so each of these blue dot is y of x given data subset. And then h of x is the parameter, think of it as parameter in high dimensional space. So the bias would be like if we take the mean between this, this will be the bias squared. And then the variance is actually, it's not going to be very clear. So let's say the variation between around the mean of the different estimates. So we can think of basically mean of the estimates here is expectation over different data subsets of an estimate over a particular data subset. Okay. As we said, the second term upstairs is noise. So we just decompose the first term. And the summary for this high-level picture is that the expected loss, which is denoted by E of L here, is a combination of bias, denoted as the average distance from h of x from the average of the estimates over different subsets, and variance of the, basically it's the average deviation of each estimate with respect to its mean across different data subsets. Note that the expectation over different subsets are consistent. It appears in both the bias and the variance term. And then in the noise term don't really depend on different data subsets. Therefore, the expectation over curly D don't need to appear here. So the expected loss is a combination of bias, variance, and noise. Furthermore, right, so we're going to now look at some examples to make this expression more intuitive. This is, again, example from a book about the sinusoid. So what controls the bias and variance trade-off? Here is actually the regularization parameter lambda. Right. So these, in reality, it's hard to come up with multiple data subsets that are sort of randomly sampled. But since this is toy data, they generated 100 data sets, each having 25 data points. Right. There are 24 Gaussian basis functions. So the model complexity are all the same, or how expressive the models are all the same, 24 Gaussian basis functions. So here's the result for fitting, right? So from last week, we know that small values of lambda like large values of lambda leads to simpler models, right? And small values of lambda encourages more expressive models, right? So in this case, note that the values of lambda is different from what we were looking at last week, like 18 or minus 18, because the linear, like basis functions here are different. And the data size sizes and so on are different. So it also says that lambda is a hyperparameter that you can't reuse from one fitting to another. So when lambda is big, the model is simple, the bias is, so here the bias is big, but variance is small in this first graphic, where we essentially eyeball the variance as in the difference between different fittings, right? In the last case, where lambda is small, the bias, basically the ability to fit the sinusoid, target sinusoid, is pretty good, right? But variance is big, meaning there is lots of wiggling and deviation across different 25 samples of the data set, right? Moreover, if we plot the learning curve against log of lambda, the hyperparameter, what we can see is, because it's a linear model, we can write out the bias term and variance term. We can see that if the whole test error, as we saw last week, goes up as there is a sweet spot for test error around here, right? But it goes up on the right-hand side because the model has higher bias or becomes too simple, right? And that was what we observed last time. What we didn't observe is that there is this trade-off between bias and variance that constitute the test error, right? The variance goes down as lambda becomes bigger, but the bias goes up as lambda becomes bigger and the model becomes less expressive. And of course, as we saw so we can think of basically the bias and variance combination as one component that contributes towards the test error, and what goes in between is noise, right? So the minimum of bias and variance occurs close to a value that gives minimum error. That is because noise don't change and they're inherent in the model class that we chose. So here is a note. Again, we keep encountering bias in two different senses in this class. One is the weight vector for the constant feature or basis function. It's called bias. It has no negative connotation. And in here, we are encountering bias in a different fashion. It's basically the deviation of the average of the estimates across different data subsets to the true model. So you can certainly say that high bias is not good, but compared to the statistical literature, like we said last Friday as well, we also shouldn't strictly interpret this as a word with negative connotation, because as we saw here, there is an inherent trade-off between bias and variance, and sometimes there is a reason to make a particular choice that has a particular bias value, rather than just trying to drive bias to 0. In this case, as we see, if we drive bias to 0, variance will go up, right? There is a deeper connection between regularization and model complexity that we're not going to be able to cover in this class. So that's that. So again, there is a trade-off between bias and variance in general. If we're not fitting linear models, but we do have control of the synthetic data generation process, we could actually visualize bias and variance intuitively using something like the bullseye plot. right? So although bias and variance are hard to compute analytically, it is a useful way of thinking to diagnose our machine learning models. So the takeaway, again, is expected loss is bias squared plus variance plus noise. Noise cannot be removed. And as the book says, in order to analyze the bias variance decomposition, many data sets are needed, which are not always available. The exception is that when we are trying to, say, diagnose our new fancy machine learning model that we're trying to write a paper with, then we can essentially generate infinite amount of data. It's super useful for diagnosing, let's say, whether or not the new fancy model is not working, or whether the optimization procedure, say stochastic gradient descent or some other fancy gradient descent, is not working. So that's all for today. We covered linear models for regression. We told you a story about why linear models. Hopefully we'll come back to like essentially modern fixes for linear models that are more transparent and interpretable in the next week. We talked about representing input data as basis functions. We talked about maximum likelihood that are essentially the same estimate as least squares. We talked about how to think about it in vector space and regularized least squares. And we spent some time talking about bias and variance decomposition. So that's today. So today is fairly mathematical, I would say. And this Friday is also one of the more sort of like mathematically involved lectures. But I think the meta takeaway from today is being able to carry out maximum likelihood estimation using a small subset of vector calculus is useful. The takeaway for this Friday will be that being able to reason about Gaussian distributions will be useful, especially if you're like pursuing further research or advanced topics in machine learning. We briefly looked at Lagrange multipliers, and we are going to basically keep looking at multiple ways of looking at linear models that connect to each other, which is part of the beauty of statistical machine learning. So that's all. Any questions? I'm going to pause the recording for now.
Can you give us